Come light it up, I'm ready to go. Come light it up, come light it up, I'm ready to go. Come light it up.
Hi everyone. So my name is Ricardo Cardans. I work for Talkdesk, and today I will be presenting a galactic journey, like I told here in the slide, from the Beeland to the Icehouse. I hope you like it. And of course, in the end, I will be leaving my email so that if you want to reach out and clarify anything, please do. So a little bit about me. I will not spend too much time on this, but I'm based in Portugal. I'm working remotely for the past few years. I've been working on banking, insurance, telecom, retail, and some government, which I can talk about. And I'm currently at Talkdesk for 5 years now. A lot of time. As you can see, I was a lot younger in my image than I am now. But well, I still can do it. I started in the trenches from the trenches to the lieutenant room, and now I'm currently focused on the data platform architecture here at Talkdesk. So a little bit about Talkdesk, in case you didn't heard about, it's an AI-powered CCaaS platform, contact center as a service. We are on a mission to rid the world of bad customer experience. We have been on Forbes Cloud 100 for the past 6 years. So I think it's worth mentioning that this year we were named also the best AI company CEO, and we are a leader in G2 for contact center. So you have the links if you want to know more about the company, please reach out as well. So without further ado, I will talk about our data journey here at Talkdesk, at least for the past 5 years. My intent here is not only sharing the secret sauce or the successes, but also the challenges that we have in every iteration. I hope that this will probably save you some time in case you are considering using a lakehouse architecture. I will share some of the iterations that we have done, things that worked out just fine, things that didn't work so well. I hope this inspires you in any way, or at least saves you some work and some trouble. So just a little bit about what kind of products our data platform produces. We have two main products, Talkdesk Live and Talkdesk Explore. Talkdesk Live is basically a real-time key performance indicator monitoring platform where contact centers can see in real time statistics about their contact center. The information is really, really fresh. It has a second-based data freshness. This information is available through an app embedded in our product or through an API. We have a second-based data query latency, and this is a product that holds 48 hours of data. So this is a product that doesn't retain data for a long time, but it has a lot of queries being submitted every single second. So the challenge is really the query scalability on top of the product. We then have Talkdesk Explore, which is a reporting product. It will actually be the focus on this presentation, and you will understand why during the presentation. Similarly to Talkdesk Live, it's available in app and through API. This has minute-based data freshness and minute-based data query latency in worst case scenario, but it has unlimited data retention. It is a product that is quite flexible. It allows our customers to understand their data in a customizable way, and it really allows them to understand not only the data from recent time, but since they are our customers. So a little bit about our numbers. We have, this is the part of Talkdesk Live, we have roughly 500 million real-time queries per day being submitted through the product for the data from the last 48 hours, like I mentioned before. And we are able to achieve P50 of roughly 6 seconds and a P99 of 20 seconds. So we really have a lot of queries going on here. On the other side, on Talkdesk Explore, which we are calling historical queries, we have 5 million queries. It's significantly less, but we have unlimited data retention. So this means that we don't have that many queries, but it can fetch a lot of data. So it's quite challenging in another fashion. And because of that, we have a P50 of roughly 15 seconds and a P99 that can go up to 20 minutes. And this is actually something that we try to improve throughout the times, and you will understand what we have tried to make that happen. It's important to notice that in this scenario, we have bursts of roughly 2,000 queries running in parallel. So it can be quite challenging as well to have 2,000 queries running in parallel for unlimited data retention and customizable data fetching. So our lake after compression holds hundreds of terabytes. We should be soon reaching the petabyte scale. So I think these numbers are, of course, not the biggest that you have ever seen, probably, but they are big enough for having some challenges. So now I will be talking a little bit about of our architecture and how it evolved in the past few years. It all started not with the Big Bang, but with an event-driven architecture. So for the real-time data streamers over there, this is likely something that you will like a lot. Since its conception, the data platform architecture has been based on an EDA architecture, which allowed us basically to scale quite fast, to increase the number of products quite fast as well, because everything that is done in our product triggers an event, and this event can be consumed by any app and by any microservice, and that really happened, and that really allowed us to scale fast. So in the beginning, we had this ingestion platform, like I'm going to simplify in this draw, where we basically receive the events from RabbitMQ, and then we have a bunch of applications that are here simplified in terms of naming. One application that bridges the events to Kafka, so that moving forward from this point in architecture, it will be scalable. Then we have an event router that basically picks up the events, the raw events, and starts to routing them based on their data types and their event types as well. Then we have an event processor, which is basically an application that starts enriching the data, fetching data from lookup stores, enriching the events, and then these events are forwarded to a last application that eventually leads the data to MariaDB. This was our first architecture version, and it enabled us to have Talkdesk Live working, and it went for a couple months. So at this time, we already had a couple of first principles that we should take into consideration when designing a data platform. We had in place everything related to backup and recovery. We had security in place. We had processing scalability, because since beginning, we chose technologies that allowed us to scale throughout the times, like Kafka Streams, Kafka. And we had real-time data availability. So with this architecture and writing in MariaDB, we were able to provide real fresh information for our customers through our products. But soon enough, we realized that our customers were not only interested on what was happening now, but also on what's happened a lot of months ago. So this started to evidence that we had to have a capability to process and analyze historical data, which we didn't have in this phase of the architecture. And also, we soon realized that we'll have to put together data from multiple teams. So eventually, we did understand that we will have to support here some kind of data federation, so that we could just quickly plug and play data and offer that for customers for long-term searchability. And because of that, our architecture started to evolve to something that looks a lot like a Lambda architecture. As you can see, the ingestion platform that I showed before remains the same at this point, which we call now the speed layer. And then we start building up a batch layer within the ingestion platform, where basically we still want to offer the data with as fresh as possible. So we kept MariaDB so that we could stream the data really quick, but we also want to show historical data. So eventually what we did was to put the data in both places and then introducing Trino in our architecture, which enabled the federation part that we were looking for. So for our customers, the experience that they were getting in Talkdesk Explore was that when they searched data, the recent data from the last few days was available through MariaDB, and the real whole data before the X days was fetched from Hive. In the background, we had a process that we called data consolidator or event consolidator that basically used a bunch of AWS services to every day move data from MariaDB to Hive. And then Trino would stitch together the data to present to the customer. So this was really the point where we started to have the capability of keeping unlimited data and serving that through our products. So looking at our previous capabilities that we didn't have, we now have in this point in time. But we started to have customer growth, not only the number of customers, but the amount of data produced by our customers. And we soon started to reach the reasonable cost effectiveness of MariaDB in terms of write throughput. And so we didn't have the capability without performance degradation, and we were basically affecting the freshness of the data because we were not being able to cope with the write throughput. So we started to look around on technologies that would allow us to scale the writes, and eventually we added ScyllaDB. For those who don't know ScyllaDB, it's essentially an alternative to Cassandra, but it's quite similar. It's a NoSQL database that scales really well in terms of writes. And so for those tables or data sets that were really intensive on write throughput, we start diverting the real-time traffic, not for MariaDB, but for ScyllaDB. And then we adapted our event consolidator to also move data from Scylla to Hive for long-term storage. So once again, we used our good friend Trino to stitch everything together. In some cases, data from Scylla and Hive, and in other cases from MariaDB and Hive. So at this point, we were able to scale the writes that we need. And we started to have different requirements now from an internal and external perspective. So in one hand, we started to have a high demand for policies and procedures for managing data availability, usability, and integrity, like requests for data repairs. And on the other side, we have to comply with relevant regulations and standards like the GDPR that in Europe are taken very seriously as they should. And so we started to work around the architecture that we have to start complying with these needs. And basically, this drawing is the same as the before, but now we have new processes that start to pile up to manage data in terms of self-service data repair, self-service GDPR, and other maintenance processes that you may imagine. And as you can see here, we started to be able to comply with the regulations that we need to. We gave our internal teams a way to manage their data in terms of data repairs and GDPR and so on. But you basically need to know that at this point, our internal teams were basically dependent on us. So if a team wants to have a new table or new data set or data model, they would have to depend on applications and deployments made by the data team, which was starting to make the experience not so smooth and not so scalable so that we could easily deploy new information, new data for our customers. And at the same time, because we have this mixture of databases, we started to have issues with read scalability. in a cost-efficient way. So basically, we were able to provide data very fast, but and then in an easy way with Trino, but with the effectiveness affected. So we started to look at what was the big issue here. And of course, first thing we have to look is where is the data kept for more time? Which storage layer has more data? And the answer is Hive. And Hive is a table format that has been around for perhaps 10 to 15 years, if not more. And it has the proofs given. There are quite good things about Hive. It's comfortable with everything at this point in time. It supports all kinds of file formats like Parquet or JSON, CSV. It's a simple catalog implementation for easy data discovery. It has some basilar features that are the base for everything, like pruning and push down. But there are things that are not so good. For example, data and metadata are stored in different systems. Typically, data is stored in a distributed file system or blob storage, and the metadata is stored in relation databases. This introduces like single point of failures in multiple points. It's harder to accomplish SLAs with this kind of setup. The metadata layer is quite poor. Hive does keep track of table partitions, but it does not keep track of data files. So the query planning is often suboptimal because in every query, you have to try to select the partitions that are relevant, but then you have to list the files that are over there, and that takes time, that takes IO, that takes money. And the statistics are quite limited and stale. They need manual refreshes. The predicate pushdown depends mostly on the underlying file format to work on. Like Parquet gives statistics that Hive or Trino eventually use. And like I said, there are higher costs on pay-by-request stores like S3 because every query needs to basically check every file that is available before start planning the work. And scaling the Hive Metastore server is not a trivial task because it's a drift-only catalog implementation, handles poorly without partitioning cardinality, and it's not very easy to create a distributed load on a Metastore server. So there are also some things that don't make Hive a particularly attractive format for those that are most used to relational databases. For example, Hive by default doesn't have ACID support except with Hive ACID, but Hive ACID requires ORC as a file format. Is compatibility is limited in these constraints, limited enterprise support, and limited access control due to inflexible catalog implementation. So it has limited DML or DDL support. Evolving a table is typically something that requires to rewrite an entire partition. Abstracting data requires complex syntax and heavier computation. And well, it's simply not designed for streaming. Small files are hard to rewrite. Concurrent writes lead to uncertainty on data correctness and quality. Because with all these processes starting to be made available, like repair, GDPR, moving data around to Hive, it's quite easy to get in troubles like these ones that I saved across the time. For example, where's my call record from a few minutes ago? It's still not here. Well, where is it? Or things like a simple operation like adding new data, adding a new partition takes a lot to do. Queries are getting slow. We need to rewrite the table with the new partitioning. Why this much IO to fetch a few dozen of rows? I need to repair my table. I will probably need to rewrite it. So Hive is a quite good format, a cheap one, but it has limitations on the way we interact with it. It's not easy to modify data that lives in Hive. And because of that, we started to look around alternatives. And when we start to do that, which was roughly in 2020, if I'm not mistaken, we started to look at our options, and there were two that really popped out at the time, which were Iceberg and Delta Lake. And I'm not going to do an extensive comparison between both of them, but I will just say that at the time we chose Iceberg because it really seemed the one that was truly open, truly independent on any vendor. There were a few vendors starting to support the format, but not in a locked way. So at that point, that seemed the way to go. And this was a format that basically solved the limitations that we were observing with Hive. Like it had ACID compliance, supported all the file formats that we are used to. It had schema evolution. We could simply add new columns, change data types without rewriting the entire table. We could actually evolve the partitioning layout without rewriting the table. And we could do operations like update, merge, delete without rewriting big portions of data. So essentially, we evolved our architecture to look something like that. If you look at this, the big difference is that we basically opt in on Iceberg as the unified storage layer for our data. And in the ingestion platform, we dropped some components and we developed an SDK, an internal SDK to write data to Iceberg, mainly fetched from Kafka. And eventually we migrated our processes to work with Iceberg directly. And of course, we had to keep up with the maintenance that Iceberg also requires, which is expiring snapshots, rewriting manifests, compacting data files. But all of this made within the AWS cloud managed services. We had at the time, there were no built-in, or there were no really documented approaches to do this. So we eventually built our own solution, which was something built upon step functions and event range to basically spin up EMR clusters and compact the data in the tables. And of course, our loyal Trino here, still serving the requests for our products. And by now, we had solved these issues. So we have the capability to the teams to develop new data models without depending on the data team, because we introduced Flink with a decentralized development approach. We did solve the read scalability issue because now we have a unified storage layer at a cost efficient way, because we didn't have to get different databases to hold the data that would be served by the same product. Don't get me wrong, I'm not saying that we killed federation. I'm only saying that for our products, we went to a unified storage layer approach. But of course, internally, we still have to put together data from different teams from different databases. But for our product, we did opt in by Iceberg in this case. Well, that said, we were in a much better point than we were before. But we now have to lead with different issues. And those issues were basically the architecture simplicity. We did simplify the ingestion platform, but we end up building a lot of services to do basically the same, which is running SQL queries or SQL maintenance operations. This was probably one of the most concerning ones, which was the predictable performance. So we have been users of Trino for a couple of years now. And while it served us really well, the open source version, we didn't have quite good auto scaling capabilities on our side, which means that every time a new team added a new data set, or the customer base grows, or within a data set there is more usage, the most recurrent issue was that eventually our setup was not enough and the auto scale did not kick in time. So basically we did have a lot of incidents because we were just not fast enough adapting our infrastructure to the new load. So our concern here was, if we keep adding more data either to Iceberg or any other federated data source, we have not comfortable to say that we have a predictable performance because we know that a slight adjustment can cause the P99 to spike. And this was something that we really want to solve. And then there's also the question of start working more seriously around user access control to build fine-grained policies that would match the functionality that Iceberg provides, like being able to specify that this user can run updates but cannot run deletes. This kind of fine-grained access control policies were also making sense. And also the experience of interacting with the data. We usually we used tools like dbeaver or the Trino CLI, which are great, but for business people, for example, it's not really interactive. It's not a place. We didn't have a place where we could just find all the information the company has, and that was something that we also need to work on. Then auditing and quality processes were also they were in place but limited, and we also want to improve that, like which user did what at what time. This is also something that we really want to work on. And then eventually we start to look at enterprise solutions that could give us these functionalities that we were now looking at, and we find Starburst Galaxy, which basically it's a lakehouse platform that really ties together with Iceberg. And I will tell you why. For example, for the maintenance that we used to have with 6 AWS services, we can now just use a simple UI with a few toggles that enables the maintenance on each table that we have. The data repairs could easily be replaced with SQL jobs that basically enable to schedule a SQL execution for a given query. The same for GDPR, which is also achievable with this SQL jobs functionality. We have data quality built in, like the ability to analyze our data and look at quality trends for each column, if it is increasing, if it is not increasing, defining our own quality checks. Also automatic PII classification, which is quite important for GDPR. The privileges around the tables, and also the auditing for who is doing what at what time, which cluster, what is the query ID, and how much time did it take. So, and mostly, we did find out that Starburst could give us what we were looking for Talkdesk Explore, which is the predictable performance. So, like I said before, every time we have a new dataset or we have more customers using the product, it was quite hard to keep the performance within a value that we could safely publicize and say, well, whatever it happens, we can keep the values within these boundaries. That was really hard for us to say. But with this new architecture, we were able to accommodate these changes, and we could just see the auto-scaling capabilities of the platform really working in real time. Like when a spike of the number of queries happens, the auto-scaling really happens at the same time, and everything works just smoothly. This is basically something that I took from Galaxy website. You can see in detail, but this is basically showing up the data plane that we can get with Starburst Galaxy in a Iceberg and Icehouse context. So we do have a lot to work with, and we have data maintenance automatically set. We have autonomous indexing and smart caching, auto-scaling capabilities, fault-tolerant execution, and then the part of fine-grained access control, resource management, and data observability as well. This can, of course, be the base for our products and for our BI and AI teams to have data from all the company in a single unified place. And to not take only my word for it, I'm going to show you some numbers. This was our P99 with the twin open source version, and then the comparison with Starburst Galaxy. As you can see, and I shared in the beginning of this presentation, the P99 used to be around 20 minutes, and it's now set to be 3 minutes in our trials with Starburst, which corresponds to an 85% improvement. It's quite significant. A P95 with an 83% of improvement going down to 2 minutes, and a P50 with a 33% improvement going down to 10 seconds. So as you can see, this is the part where we can really count with the predictable performance. When having new data sets and having new customers, we can really keep the performance within the same boundaries without having these spikes that basically mess up with our metrics. And this is also the result of the observation in our trials, which we saw the error rate reducing by 150 times. It's not percent, it's times, going down from 1.5% to 0.01. And then this actually is equivalent to a failed query time in a nearly projection, going down from 6 days to 1 hour, which is a 99% improvement. So these numbers are really quite good. It also matters to reference what this means in terms of maintenance effort for our teams. So because we are basically simplifying not only our products, but also our internal ETL platform around Starburst Galaxy, this will allow us to reduce the number of our applications by 14 less applications to maintain. It's quite a lot. And to also cut on 6 cloud services that we were using specifically for services and capabilities that Galaxy can offer out of the box. So this is really what I have for today. I hope I have shared things that can be useful for your journey as well for the adoption of the Lakehouse. And if you want to know more, if you want to clarify anything, just reach out to my email, which is here. Thank you.